Hello everyone and welcome to our 25th lecture, Application of Derivatives. So today's lecture may be a bit shorter, I don't know yet, but we will only cover the uses of derivatives in stuff that we have learned so far, that we will learn later in physics and even something for the next few lectures. So since I forgot to show Leibniz notation for nth derivative in previous lectures, I'll show it here. I think I use it later and I don't use this one, the correct one, because this slide is being recorded as I'm editing, because I noticed I forgot this before. So for nth derivative, like second or third, the formula changes to this, where we put the exponent on the d on top and on the variable with respect to which we're deriving, in this case the x. So for instance, our second derivative would look like this. So d to the power of 2 times f of x divided by d times x squared. So that's the second derivative of function of f of x, okay? Hopefully this shows how it's supposed to be used, because it's used incorrectly later on in the video. So one of the uses is to estimate a value of a more complex function by using a derivative of the function. So it's called linear approximation, and let's see how it works. If we set f prime of x as the derivative of f of x, yes, f prime of x is the derivative of f of x, yes. Then f prime of a, so the derivative of the function at x equals a, will represent a slope or a tangent at that value. So basically the derivative at a certain point is the slope at that point, as the basic definition goes. However, for this property, we will be using that tangent to predict the behavior of the function. So for a value close to the a at which we look at the slope. Like we see here, the blue tangent has a similar a collection of similar y values in a certain deviation from this point. So up to here and here, we can say that if we put a certain x into the linear one, we get pretty much the same y as the curved one. So basically, we will be using the derivative to try to estimate the value that a more complicated function has at that value. But don't worry, we see. So this formula of the derivative of the function of a times the difference between the nice a value and the x at which we calculate the y, so at the x at which we're estimating the y, plus the value that the normal function has at point a, so the nice a. It will give us an estimated y value that the function would have. The a is the value close to the one we're solving for, and x is the value we are solving the y for. So a and x are supposed to be close together. A is usually a nice number, so some that gives us an easy to solve result. For instance, if we had to calculate the value of natural logarithm of 53 divided by 99, we would take a, so the nice number, as 1/2, and x as 53 divided by 99, or something like that. So that sounds complicated and all, so let's see a practical approximation for a function of natural logarithm of x. So this is our function. Let's say I want to be able to approximate the values this function would have near x equals 1. So at values like 1.1, 0.9, etc., basically any x that's close to 1. So this is not the correct markings yet, I'm just deciding what my values will be. Now from last time we remember what the derivative of natural logarithm is. If we don't, we will use the table, and the table says that the derivative of natural logarithm is 1 divided by x. So we will insert in our x, or in this case a, since we assumed 1 is the value around which we will be doing estimations. I'll label stuff first, then insert the right values into the formula up top. So I changed the x to a because our a in this case is the nice value, so the one that's easy to calculate for. That's why I adjusted it. And then I put these into this formula right here. So the derivative of a is 1 divided by 1. Then we have this part which we can't solve just yet because we don't have an x. And then we have the function of a. So let's put in the derivative part first and insert the a here, and then we add together the natural logarithm of 1, because, well, insert a into it. We know that 1 divided by 1 gives us 1, and if we had a logarithm of something like no matter what the base of the logarithm is, if the value inside it is 1, we know that the result of this part must be 0, because the result of exponentiation being 1 means that the exponent must be 0, so if the base isn't 1, of course. So the base is e in this case, so to what power must we raise e to get 1 at 0? So this part will, disappear because it's 0, and we're left with this. Now we just multiply this together to get our linear approximation, so a linear function that will give us an estimated value of x inserts around our a. So when I say close to the value, I mean very close, and let's see just how close that is. So I could have used the values lower than 1, 2, but it'll be easier to compare. I also added an extra column at the end with relative error, which of course we still remember the formula, but if we don't, I wrote it on the side just in case. So the orange is for the markings, so x values column, the approximation column, the real value column, and the relative error column. This is in percentages, that's why the 100 is here. So this is all 4.9%, 9.7%, etc. So in the dark green is the value at which we set the approximation, so the relative error will be 0, obviously. But as we distance ourselves by 0.1 unit, so from 1 to 1.1 as x, we see that our relative error is already almost 5%. Moving to 1.2, the error is already at like 10%, meaning 0.1 deviation from this value. So this difference is the difference between this value in the x column and the a value, which we set for 1 in this case. And we see if we go too far, this error becomes a lot greater as we can compare the values. The approximated y value is 0.1 for 1.1, but the real one is 0.0953, which is close enough, I guess. I mean, this is just a visual representation of how close you have to actually be to the value to make sure that it gives you an accurate approximation. So while it does depend on the function and the position at the function, this still gives us a handy look into how this kind of works. For some graphs at certain values in them, we will be allowed to deviate more from the selected x. On some, even a 0.2 difference may be too much. But stuff like this allows physicists to get away with saying stuff like sine of x equals x, which we all know is only true for small x values. Well, hopefully we know that. But yeah, point of this part on how to use it for linear approximation is this formula, where a is the nice value that has an easy to solve result. For instance, we know what the logarithm of 1 is. That's easy to solve, so any value a next to 1, it can be used for approximation there. If we have 1.6, we would have to find a point that's easier to calculate close to that. But then again, usually when you have linear approximation, you get something that's nice to approximate or easier to approximate for. Now, moving on, the second thing we can use the derivatives for, as promised, are local maxima and minima. They are also called critical points. These critical points occur when the value of the derivative of the function equals to 0. So that's when you find the zeros of the derivative, and that means the original function will be horizontal, even if just for a single point. But that's where we get minimas, maximas, and zeros. But to tell the difference between maxima and minima, we need our second derivatives. I will be using the left marking, as PowerPoint likes to troll me with sometimes and put the superscript into normal lines, so this 2 bracket would just appear normally. So yeah, now when we get our second derivative of the function, we of course need to find the zeros of the first derivative, as those x values are then put into the second derivative. And then when we put them in, we can get either of the 3 results. The value of the second derivative after the insert can be lesser than, greater than, or equal to 0. What does which give? Let's consult our professional friend, Desmos. So I graphed a function of sine of x, but I added a limit, so This brackets determine that the graph will only be defined between, for these x values, between 0 pi and 2 pi. So one interval. So we have one maxima and one minima, or maximum and minimum. I marked them because I can see them, but let's see the actual solving process. So if in case you don't know where and at what values they are, I will take the derivative of this function and mark the zeros. So we get cosine of x, hopefully we recognize it, the purple lined one. I mark the zeros as blue points now that we have established that there are two zeros on this interval. We know that there are two critical points, so let's take the second derivative to see which ones they are. So you see the first zero is here and the second zero is here. And as you can see, they fall in with the maximum and minimum. Now, okay, Desmos also allows this. I don't know if I say this later. You can use this notation to mark the derivative of a function, and it will not display the formula of the function, it will just draw it, okay? So it draws the derivative. So I will repeat that and use the derivative of sine of x. And as we know, the derivative of cosine of x is minus sine of x. As we can see, it's basically the original red function mirrored over the x-axis. Now that we got the function, we would insert our zeros from the first derivative, so the x values we got before, and then observe what the sign of the y value is. We see that the first zero gives us a negative y, and the second zero gives us a positive y in the second derivative function. So our first zero is negative, so the first example, and the second zero is positive, so the second example. I marked the examples here, and they're both colored blue, so it's easier to see them later. Now let's look back to our original function, either here or scroll back, but I will mark it over the red dashed line, which is our first function, so it's easier to show. We see that the first zero is at the position of the maximum, and the second zero is at the position of the minimum. So we're looking at zeros of the purple function that are equal to the critical points on the red function and at the signs of the black function, okay? And we see that the negative sign on the second derivative falls with the maximum on the original function. And we see that the positive y at the second derivative falls together with the minimum of the original function. So we see that when the second derivative is lesser than 0, we have our maximum, and when the second derivative is greater than 0, we have a minimum. So if I were to sum it up in one line, I'd sum it up like the line colored in green. So first you find a 0 of the first derivative. So the x where the first derivative equals 0. Then I would insert this x into the second derivative of the original function, and then the result of that determines whether a function has the original function has a maximum or minimum at the x from the first derivative. This means that when a second derivative at the 0 from the first derivative gives a negative value, the original function has a maximum at that value. While if the second derivative gives us a positive y value when inserting a 0 from the first derivative, the original function has a minimum value, as we can see here. So yeah, that's basically it. Find the derivative of the first, find the 0 of the first derivative, insert into the second derivative. Negative result is maximum on the original function, and positive is minimum on the original function. Hopefully this is clear enough. As for the last option, sadly that one means the test is inconclusive. So yeah, so let's try it out on an example. I see that I forgot the example for linear approximation. I did give you a visualization. So if you want homework, you can do some linear approximation on your own, or just stick by for the mini test. But yes, let's try to solve this in an example. We have some polynomial, so let's get our first and second derivatives. I will be using the power rule, so 3 in front and reduce the power by 1, 2 in front and reduce the power by 1, and then the constant disappears. We get this. I factor out 3x, so it's easier to find zeros later. Then I'll take this part and take the derivative of it, so we get the second derivative, carry the 2 in front, reduce by 1, carry the 1 in front, and x disappears, because x to the power of 0 is 1. And we get our second derivative. Now looking at our first derivative, we have two critical points because we have two zeros. First one is at x equals 0, and the second one is at x equals 2. If you don't know how we got to this, check out the polynomial functions video, which is, I think, where we explain this. Then I will insert these zeros into the second derivative function. So the second derivative of the function at x equals at x1 and the second derivative of the function x2. I have this one copied over, insert the x values instead of the x, of course, and then I get -6 for the first one and +6 for the second one. And we know that the negative sign in the second derivative gives us a maximum, and the positive sign in the second derivative gives us a minimum. So we know we have one maximum, one minimum. The maximum occurs at x is 0, and the minimum occurs at x is 2. And this is our graph, and we see that it is true. As for the name, local maximum or minimum just means in its region. So it's not necessarily the highest point in the graph, but in a certain proximity. Because as we can see, this part goes higher. So this is a local maximum. It would be a global maximum if it was something like -x², where there is one point that is at the top and no other point gets higher. But we won't go into that. I could do one more example of this, but I think this one actually clearly explains it. If it doesn't, you can please go ahead and ask in the comments. I can make a special short video to explain concepts or examples, solve more examples, so you guys can understand anything we're working with, just in case something isn't clear. Now, building on the previous point, we can also use that rule to determine concavity. So we know that minimum is like a U shape, while a maximum is the opposite, so falling down. So concavity in math, I'd say it's like concavity, and cavity is like a hole, so more like a U shape because you dig a hole from the ground, you know? And since you dig it out, it's shaped like an U, and I guess concavity here would refer to which direction the hole is facing, so away from the bend. Meaning, if it's U shape, so the whole part is facing up and the bend is facing down, that's a minimum because the lowest point is facing down. So the second derivative, greater than 0, gives us a minimum, meaning it's concave up, because that's where the hole is facing. While we have a maximum, it's concave down because the hole is facing down. This changes slightly in physics, because they are such divas, they always want to be special, but we will get to that when we get to that. And that's probably when we cover light and optics. Oh yeah, I have to make a roadmap for physics soon, huh? Anyway, now I know that we all hate the French and whatnot, but this French guy, Gillon de l'Hôpital, however you pronounce his name, basically L'Hôpital, came up with this wonderful rule for solving limits using derivatives. So I think last time we had an identity, well, last time, 4 times ago, that we couldn't really get because, well, we didn't have this rule, but now we can. And we can use this only when we have indeterminate forms of 0 divided by 0, infinity divided by infinity, or negative infinity divided by negative infinity. So if our limit of function x divided by function, f of x divided by g of x would give us 0 divided by 0 or any of the 3 here, then we can use the L'Hôpital's rule, which states the following. If we have this indeterminate form, the limit when x approaches a of f of x divided by g of x will be equal to the limit where x approaches a of the derivative of f of x divided by the derivative of g of x. Well, I wrote the derivative in 2 ways because I don't know how easy or clear this prime marking here is, because there are tiny lines and sometimes it's hard to see. So I added d over dx for to make it truly make sure that you can see the point. So if a limit goes towards this indeterminate form, either of these, you can take the derivative of each of them and insert them instead of their respective functions. We don't have to use the rule, the quotient rule here, because we're not taking a derivative of the quotient. We're taking the derivative of each individual function and just placing it back into the place. So let's solve an example so you see what I mean. The limit of sine of x divided by x when x approaches 0. We all know it's 1 now, but with this rule we can actually see why that is. So of course we first have to test it, insert x as 0, and we get 0 divided by 0, which of course we now love to see because we can use our rule. So to use it, we take the derivative of each of them, and then take the ratio of the both derivatives. So the derivative of sine of x divided by the derivative of x. We know using the table that the derivative of sine of x is cosine of x, and the derivative of x is 1, giving us the limit of our problem equals to the limit where x approaches 0 of cosine of x divided by 1, which is basically just limit of x approaching 0 on a cosine of x. Now we again follow the rules of limit solving, so inserting the value as the x. And we know the cosine of 0 is 1. So this is how you would get this identity that we love so much. This means and shows that of course our limit of sine of x divided by x when x approaches 0 does indeed equal to 1, and we now know why, since we laid that knowledge in the limit lecture and we couldn't skip ahead that way. It is important to know that if you get 0 over 0 or infinity over infinity, whatever again, after using L'Hopital's rule, you can use the rule again and again and again. So even if you have used the rule already, you can use it as many times as you want or need, but only as long as the result when inserting the value is one of these three that I have listed before. So 0 over 0, infinity divided by infinity, minus infinity divided by minus infinity, whatever. Okay? So if this one gave us 0 over 0, we could use it again. That's hopefully clear. Since this is quite a good rule, I'll show one more example before we move on to physics. So let's solve this easy example. The limit of this rational function as x approaches infinity. Well, we could analyze in terms of rational functions and find its asymptotes and whatnot. That helps sometimes, but since we learned this neat trick, let's use it. But first, don't worry, I won't take a selfie for those of you who had flashbacks of 2015. I will, however, try to solve it, solve the limit normally. Ah, okay, this is bugged again. So I'll insert the supposed infinity. So I'll assume infinity is a number, infinitely greater than any actual numbers. And since it's infinity, squaring it won't change it much, especially because it's a concept and greater than infinity simply won't exist for this sake. It stays infinity. Same for multiplication. It will not significantly change the value, meaning multiplication quote-unquote disappears. So we get this. And I assume we all see that adding a drop of water into the ocean won't change its volume significantly, right? So we get infinity over infinity, meaning we can use L'Hopital's rule. So I took the derivative of each side, inserted them back in, and then got 6x divided by 10x. So derivative of this, carry the 2 in front, carry the 2 in front, constants disappear, and you get this. Now we can cancel the x's out, and we get 0.6. And this is the limit of our problem. Well, we could solve it by inserting a super large number like 1000, which is not that large, but still. But yeah, this also helps. This is a very easy way to solve stuff like that. Now, I know we haven't really done anything from physics, so I'll take it slightly slower and foreshadow how we will do stuff in physics. So let's say we all know that we can write position or distance as a function of time. So as time changes, so can some item's position. So let's say I put a ball on the ground. Its position can change as time progresses if something acts upon it. If nothing happens with it, so if its position doesn't change through time, it's constant. But if its position does change as time moves, so for instance, if I kick the ball, its position will be changing as time goes on. So if I were to graph it, So let's say the ball is still, so its position is 0. And then at some point I kick it and its distance is gonna increase, okay? So since this is a function of sorts, we can try to take its derivative. And this marking with the prime can be confusing as to what I'm talking about. I'll rewrite it as d over dx, or in this case, d over dt. And we don't have to do much. This gives us a change of position divided by change of time. But so how does our position change as time progresses? And that sounds familiar. And of course it does, because this is a formula for velocity. So how fast an item is moving can be determined by dividing the change in its position with the change of time. So if a ball rolls 5 meters in 2 seconds, so we would divide 5 divided by 2, we would have our average velocity of 2.5 meters per second. I did say velocity for a reason, which we will cover at the very first physics lecture, which will fall as math 1 before last one, yes, which will be the vectors, as matrices, or matrix, will be the last one, since we kind of need vectors for them, but vectors first in physics are kind of a setup, helpful for working with formulas and explaining some. Until then, I can technically say either of them, but I'll try to use the correct terminology to ease you into it. But yes, now we have our velocity as a function of time. So change of position or space divided by change of time. Now, to see how velocity changes as time goes on, because we all know you don't have to move with a constant velocity. That's how you get faster on the highway, and that's how you slow down when you want to stop for the red light. So to see how that changes as time goes on, and we know that another word for change of speed is acceleration. Basically, so I set this formula, so d over dt, where I do this of the velocity, function of time, because this technically is a function of time, an inverse function, but a function nonetheless. So taking the derivative of this function, I will insert this instead of v. So I colored it orange on what's replacing this v. And we get, okay, yes, another intermission from the future next. So here we get ds over dt, so the change of position over the change of time gives us the change of speed. Or, well, technically it gives us speed itself, or velocity, but it's like this. And then when we insert this in here, we only insert position over time, which, why this is, we will learn in integrals lecture, hopefully. So until then, don't worry, this all makes sense. Just had to correct the note because while recording, I seemingly forgot. But yeah, that's it. I'll leave you forward to whatever I was explaining. But basically, we will insert this formula without the changes. Let's say they cancel out, as physicists like to say. The changes cancel out and we just insert s over t, which gives us, well, change of position divided by change of time squared, which, if again physicists say cancel out the d's, we get position divided by time squared, and that's the formula for acceleration. So change of velocity over time. So the formula of velocity divided by time, that's acceleration. We will stop here with the derivatives as for simplicity's sake, but I will only be working with, because I will only be working with constant accelerations, but yeah. Now usually they won't be called functions and all that in physics, but it will still be useful to know which variables are present so we can take their derivatives or even integrals, which we learn next time. So just to point it out, this is not exactly how we will be doing physics, but we will be doing them somewhere like this. So with changes and everything. I'll go more into depth how to get the formula so you can understand the background of it, because if you understand how a formula behaves or how you get it, it's easier to remember it and use it. But yes, so we will be covering integrals as the next lecture, and after that, so after the 3 integral lectures, there will be differential equations. So I won't really solve them, as I can save that for the lecture itself, but I can give you an example of a few. So this one of them would be this, where you basically have a y on both sides like this. Basically, in mathematics, A differential equation is an equation that relates one or more unknown functions and their derivatives. So in an equation, if you have at least one function and the derivative of it, or etc. That sounds confusing, but don't worry, when we get there, I'll cover it so you can understand it, hopefully. This would be some more examples, just so you can see what we can do eventually. So this is one function, and this is the derivative of some function. This is a function, this is the derivative of the function, and this is another function, just as x. This is the derivative of the function, this is a function, a function, a function, etc. So stuff like that. We work with derivatives and normal functions in the same equation, if that helps. Well, this brings us to our mini test. Thank you so much for tuning into today's lecture. It was kind of a mess, not gonna lie. But it's not much of a lecture that's needed for the progress as it is like informative or creative. You don't really need most of this stuff. Like, okay, approximate values are nice. Local extremes and minimums are like, minimums and maximums are fine to know. L'Hopital rule is insanely useful. But at the same time, you won't really be running into this as often in real life. Maybe in physics a bit. But if we get there, I will definitely introduce the formulas again, so don't worry. So yeah, best of luck solving. Thank you so much for tuning in to today's lecture. It did get slightly longer than I expected it to be, so yeah. But yeah, thank you again, and I'll see you all on our next quest. Bye!